computer. Okay, so this was where we left. We have come a long way with the labs and with the things that we've discussed so far. We are ready to, I don't know, train a model. So how can we improve our training more? That should be the question we should be asking ourselves. So an important point are the solvers or the optimization function you use. About the optimization function, we've discussed the gradient descent, the blind guy feeling the slope only. And these were the graphs. So we have a score function. This is supervised learning. We have the ground truth, the loss function calculating our model's capability by using the score and the ground truth together. So it's calculating a distance between them somehow. I don't know, depends on the type of the loss function. Then using the derivative of this loss with respect to the parameters, we update the parameters, the blind guy finding its way. This is like the summary of optimization that we implement. So the gradient descent is a good idea. I mean, blind guy feeling the slope. It's a very good idea. I mean. However, there are some problems, just like the problems one of your friends asked in the previous weeks. Remember that one? So what he said was, the blind guy is walking on a hill like this. So he stands here. Strange drawing. What he can feel is 0 gradients, which will make this 0, which will make this equal to each other, right? Then he will stop. So for that matter, he's stopping at the top of the hill. We don't want that. Well, that's why we don't use plain gradient descent, guys. So what do we use? The potential problem is, what do we use? So this is the fundamental problem, but there are other problems with gradient descent as well. The fundamental problem with gradient descent is, it is too much fragile for the immediate gradient. What I'm saying is, the immediate gradient is the actual slope that the blind guy feels, which will create an effect like, if the road is too bumpy, in optimization, we say the condition number of the loss function is too high, which means the gradients along the weight space is too noisy. Then the blind guy will have difficult time finding its way. It's going to go into a hole, then go back, trying to find a way, going to another hole. So it's bumpy and full of holes. The path that the blind guy will take will be very complex, right? It's going to get to that hole. Another hole will make him think that there's something to go there. However, maybe the thing that the blind guy should feel is like the, I don't know, the general slope. He's blind, I mean, he cannot see it, because imagine there's a slopey way. So let me just try to visualize it for you. So if the slope is like this, the blind guy will feel it. Sorry. Okay. With a nice speed. But if the slope is like this, well, there's a general slope. But because of the immediate slopes at this point going up and down, the blind guy will get slower and faster. If it is not one-dimensional, two-dimensional, maybe in a saddle point, it will just turn left and right again. We don't want that. We don't want that. That's the fundamental problem of gradient descent. The gradient descent has no mechanism to overcome this. That's why the way the optimization works in gradient descent, if this is a convex weight space where this is the higher ground and this is the lower ground of the valley, the guy will be moving just left, right, and in a bumpy way. He will lose a lot of time. That's not something we want. We want the optimization to go smooth, as smooth as it can. So the first improvement is the stochastic gradient descent. Stochastic gradient descent is very simple. Instead of a single sample, you use multiple samples together and you calculate the loss as a sum of those multiple samples. So you calculate the loss for a number of inputs using the ground truth for those number of inputs. So if the mini batch is n, this is the loss you get. Simple, you just sum them up. That's the total loss. And when you're calculating the loss, you calculate the partial derivative of the loss with respect to this sum. It is good because imagine the blind guy trying to find its way. Let's apply gradient descent and the stochastic gradient descent to the blind guy. Each step is like an iteration, right? And at each iteration, I'm sorry, I have a problem. At each iteration for the gradient descent, you take a single sample. An input comes, a gradient for the weights is designated. Blind guy feels the gradient, walks in a path. For another input, maybe it was a strange type of input, the gradient is the other way. The blind guy will turn that way. However, it would have been a good idea if the blind guy followed a slope which was like the slope created by a combination, a distribution of inputs together. That's what the stochastic gradient descent is. You take a mini batch and the loss, hence the gradients, hence the slope the blind guy feels, is calculated by, is created by a group of inputs. With this, the blind guy will be following a smoother path, right? This is called stochastic gradient descent. So stochastic gradient descent is the loss being calculated collectively for a mini batch of inputs, a group of inputs. Actually, this creates noisy loss functions too, because this is good, but it will create noisy loss functions. The loss function will change from batch to batch in this example. So what do? We need further improvements. Gradient descent was not enough. We get back to stochastic gradient descent. Now we have another idea, a very common idea that's being widely used. Stochastic gradient descent plus the momentum. It is simply building up velocity. I mean, if you have ever seen a kind of physics class in your lives, you know what momentum is. Its momentum is mass times velocity. So with your mass, you are building up the velocity from your previous velocity. So it is like blind guy when, for example, let's get back to the example where there is a slope, but it is bumpy. So it's like there is a slope. This one is the first example, and this is the second example. There is a common slope, but the blind guy will stop here. But if the blind guy feels a momentum, just like a rolling ball coming over here and just rolling with its momentum, so it can continue that trend, I would call it. It is called momentum. How to implement it? It's just simple, guys. You calculate your update rate. This is the stochastic gradient descent. The gradient is, so this is the new weights. New weights are equal to old weights plus the learning rate times the derivative of the loss function with respect to that weights, x being weights here. In stochastic gradient descent, this speed, the step size, this is the learning rate times the slope is your step size. Let's call it Vx. We put a running average of it. So the Vx is calculated with a running average where this rho is a number between 0 and 1. Okay, so it is like you are looking at your previous speed and you are taking a running average of the previous speed. So this new speed updates your previous speed, but you are having a running average out of it. That's called the momentum. So instead of this formula, you compute the gradients. You don't update the gradients, parameters directly with this gradient. You make another step here where you take a running average of the calculated speed with the previous speed, and you use that speed with the learning rate to get the updated values. That's called momentum. And when you have this algorithm, you have much smoother optimization. Actually, for all solvers, we have a momentum. Any questions about momentum? It's pretty much simple, actually. Okay. So in a local minima like this, the ball will continue rolling. In saddle points, it won't stop. It will continue rolling. So instead of this jumpy ride, with momentum, the blind guy will follow a more smooth path. Okay. Blind guy remembering what he was doing for a while. I was going in that direction, so this bumpy road shouldn't make me just confuse it. Let me just continue that. Or the rolling ball is a better example for momentum. There are many different algorithms, improvements over stochastic gradient descent with momentum. They simply make modifications on these algorithms and they use them. I'm not going to get into the details of it because there are so many. There are many ones, and these are actually, these have some, these are some links in the PDF file. You can click them. When you click them, it will take you to PyTorch documentation for that algorithm. It explains the algorithm and how you can use it. So these are all versions of stochastic gradient descent with momentum. Adam is one of the famous ones, and RMS Prop is also the famous ones. They are usually used and they're widely used. Others are also used, but anyways, the important thing is these are all solvers or optimizers. They are all versions of stochastic gradient descent with momentum. They have pros and cons in various conditions. Okay. For anybody who want to focus on this stuff, I strongly recommend you go read the documentation. You have enough information there. But how to pick, you might say. To begin with, you are going to be reusing or re-implementing a model that was previously implemented. Use it. But as a rule of thumb, people use Adam in convolutional neural networks. There are many, many advantages of it. Adam is actually a kind of adaptive speed stochastic gradient descent with momentum. So ADA comes from the adaptive part, M comes from momentum. So it's a type of stochastic gradient descent algorithm where the model can adapt its speed according to some conditions in the optimization. It has many advantages, just like it's written here. I'm not going to get into the details of this. I'm not going to read them because you're going to forget them. So as a rule of thumb, if you're working on a convolutional neural network, it's best to use an Adam. For the types of networks you're going to see in the following weeks, we'll discuss other things, but Adam is maybe the first place to start. Okay, so I think you're ready to train. You have more than 1 week to prepare your proposals. You have done a lab. You are going to do an assignment. You have gone over theoretically all the steps of the training. So if you have a good model, data set, and optimized solver chosen, you can do it. I think it is time to do it. Go see those graphs. There's nothing new for you. Anything you will come across, encounter, when you do your first training, you have the necessary information in the slides and the labs and etc. So you're ready. That's why I believe that it was important. The first part of this course, which ends with the midterm, is very important because you are ready to train. Okay? Before training, final stuff that I want to talk about. So you're ready to train. You'll get a data, but what if you don't have enough data? There are ways to enrich your data, and one of them is called the data augmentation. It is how you get more data if you don't have more data. For example, you don't need novel images. For example, you're trying to make out a system to detect tennis balls, okay? And you have only this image. You don't have to take a lot of pictures of that image. Maybe you could create a shifted version of these images, shifted in the horizontal direction, shifted in the vertical direction. They will be new images for your algorithm because the pixel values simply change. this is, I'm creating image, synthetically creating signals, samples from your training set is called data augmentation, okay? Data augmentation is actually a common technique in statistics. It's creating synthetic data from existing data. So it acts as a regularizer again, because if you do not do this, your model will overfit to only this data. When you increase that data, your model will regularize itself so that it won't overfit. It's also called in oversampling in data analysis and statistics. Okay, the good question is how to make the data augmentation, because for different types of signals, you will do a different type of data augmentation. I mean, the type of data augmentation you apply to vision, image signals, video signals will not be the same for sound signals or text. They're totally different. It depends on the input modality, if it's image, sound, or text, and it depends on the problem as well. It's a classification problem, localization problem, machine translation problem. So let's go over it. For example, you are trying to recognize a type of butterfly. So if this is the original image, you can, I don't know, detexturize it. You're losing the edges. Decolorize it, because there could be butterflies like that as well. If you're trying to detect butterflies, I'm sorry, not recognize. Flip them, rotate them, because the photographs can be taken in an arbitrary angle, whatever. So this would be a good type of data augmentation for vision. For audio, that's a different story. If you have ever studied audio, I mean, you don't have much MMI students here, but you could stretch the time, you could change the pitch. Changing the pitch means making it more lower or higher in pitch. I mean, it's inceltmek, kalınlaştırmak sesi. So you can change the dynamic range, which is the sampling rate. You can add or decrease background noise. So your system will be robust to background noise. Different types of augmentation. In NLP, it is different. I mean, for example, you're doing a machine translation. You can use some set of synonyms for some sentences. So it is also, instead of saying it's awesome, you can check the WordNet. WordNet is a digital library for synonyms for English words. You can change them and you can create these synthetic sentences. Instead of it's awesome, it's amazing, you can say. And from if you have a data set from which translates words from English to French, for example, you can create another sample from it's amazing to the same French sentence. So that it will be data augmentation. Okay, data augmentation, you somehow pulled it off, but still not enough data. Maybe you had 10,000, 1,000 data, which with augmentation, you made it 10,000 or 20,000. Never forget that ImageNet contains millions of data, and AlexNet is trained with 8 million images. So even if you augment some data into your training set, you may still have insufficient data. That's where we get to transfer learning. Transfer learning is transferring a certain capability of a model to another model where you will solve a different type of a problem. It's a common concept in machine learning, not only deep learning. So we store a knowledge in a model. We try to transfer that knowledge to another model. How we do it in deep learning is very simple, actually. I mean, compared to how you do it in machine learning, in deep learning, it's quite simple. Remember AlexNet. In AlexNet, I said that the part before the convolutional, fully connected layers, where we only had the convolutional layers and the pooling layers, was like a feature extractor, remember? And if you watched the video that I provided you in the PDFs, which was Yosinski's deep visualization tool, you'll remember that this part is highly capable of extracting abstract features. Some features, abstract faces, and remember that video. If you haven't watched it, please watch it. What is AlexNet? What AlexNet is for? Remember that AlexNet is to classify an image out of 100 categories. So you feed an image, it says some image. We done the tests, remember? It said it was a fan, electric fan to Darth Vader, that stuff. Imagine I need a network where I'm going to do another type of classification. Only 3 classes, cat, dog, or elephant. I'm trying to build up a simple system for a zoo. Whatever, that's my problem. It's a toy example, whatever. The features you need to detect a cat or a dog or an elephant already exists in AlexNet. I mean, there are other features, maybe which are redundant for this problem, also exist in AlexNet, but I don't care because I cannot find enough images for cat and dog and elephant. I don't have millions of cat and dog or elephant images, although if I do some data augmentation. Then I could use the necessary features I have, inherit them from AlexNet, and create a network for this. What I can do is, I can use the weights of this network to create another network. How I can do it is, you have AlexNet, you have it in PyTorch, you already have the pre-trained weights. You can obtain it. I take AlexNet, I cut the last layer, which is a fully connected layer of 4,000 something to 1,000, remember? I replaced this layer with another fully connected layer, which is 4096 by 3. This new layer will have to be initialized. Okay. Şimdi nasıl? İnşallah geldi. Mikrofon sorun varmış da. Kusura bakmayın çocuklar. Okay, so bir daha olursa uyarırsan sevinirim hocam. What I was saying is, you just replace this layer. When you replace a layer, you have to initialize it, because in the original AlexNet, you don't have such a fully connected layer where the weights are 4096 by 3. So you initialize them, just like you initialize our network. But the rest of the network, you don't have to initialize. Transfer the weights immediately, then train it. So the network will have to learn only this part. So maybe you could do a trick like you have very low learning rate for these layers, the ones you have transferred, so that they won't get updated much. You can even make it 0 to freeze those layers to use exact features of AlexNet. Or you can put a small learning rate where you can let the network change those features a bit for my purposes, but you'll have a larger learning rate for this part so that it would learn. This part of an operation is called transfer learning. So this is AlexNet. It was trained with ImageNet, millions of data. The models, this is the fully connected layer head, and we have predictions. I cut the head. There's a new head. I get the model. I transfer it, but while I'm transferring it, I apply a lower learning rate, maybe even 0 for this part, a higher learning rate for the new head I've created. This is called transfer learning. Okay? So how to apply transfer learning, when to apply transfer learning, how to find the learning rates. There's a nice table here, which I've taken from Stanford's slides. So this is the AlexNet. So it depends on what kind of a problem you're going to solve. The problem we defined here was, we were trying to convert the AlexNet to a 3 classification problem of animals, okay? So I think it's a very similar data set for that matter, because in AlexNet, we also have animals. A data set which is not similar would be, I think, an infrared image data set, while the AlexNet is trained by RGB images, for example. The modality, the type of data, and the number of data. So if I have quite a lot of data and a very similar data set, which is like this problem, it's the simplest case. You fine-tune a few layers, just like this layer and these layers, you'll get your results. That's the simplest case. However, things will get difficult from this point on. Imagine you don't have much data. You have very little number of data. Then maybe you will need to be more creative. This guy here proposes using a linear classifier on the top layer. What does this mean is, get the features from AlexNet, use those features and feed them to a traditional machine learning algorithm, for example, a support vector machine or a linear classifier. Because you don't have much data. Because when you don't have much data, you cannot use deep learning, it says. Okay? So that's what you do. Use only the deep learning part to extract features. Do not train the deep learning part. Get the features as they are. Use those features in a machine learning algorithm, it says. Okay, okay. But we want to do deep learning, and we don't have very little data. So I have quite a lot of data, but the data set is different. Just like the infrared example. Maybe the inputs for this dog-cleft elephant will not be RGB images. They will be infrared images. They are like images, but their modality is different. In that case, I'll have to fine-tune larger number of layers. For example, let's go over the infrared example. In the first layers, we were finding the edges, right? The filters you need to, the type of filters you need to calculate the edges on an RGB image are quite different compared to the filters you will need to calculate the edges from an infrared image. So you will have to change these layers as well and change them profoundly. Yine oluyor diyor. Demek ki mikrofonumuz bozuldu Ece. Yeni mikrofon getireyim ben bir dahaki derse. Birkaç dakikaya bitecek çünkü. Kusura bakmayın Zoom people. It's okay. Mikrofonda sorun varmış. Ya şöyle falan mı acaba? Kötü mü oturuyorum? Neyse başka mikrofon getiririz. Okay. So if you have quite a lot of data, still you might have a solution. You will fine tune a large number of layers. But if you have very little data and you have very different data set, well, you're in trouble. Most probably it won't work. But what it says is, do not do the training on the deep learning, because with very little data, you won't get anywhere training it. So the moral of the story is, if you have very little data, just transfer the features, don't train the network. If you have enough data, like quite a lot of data, try fine-tuning, updating the weights so that you will get your results. Okay, this was transfer learning. Next week, we have the midterm. And the following weeks, we are going to delve into more intricate stuff. And these are the additional references. Please check them. Okay. Tired.